My name is Fangfei. This is my teammate Boris. We work on core systems from the Facebook Boston office. Boris and I have been working together for less than a year, but that did not stop us from being crime partners and winning the core system internal award last year together.
Yes.
Today, we would like to share some challenges of continuous deployment at Facebook. So, what is continuous deployment?
Yes. Let's assume I have a service running on a set of machines. When I write a new code for the service, I'd like to send this code to all the machines, and I'd like this to be done automatically.
Correct. Continuous deployment is a process of updating software automatically. While this may sound easy at first, it can get way harder at a scale.
And to give an example of how much harder it can get, let's assume you have a service running on 10 machines. How would you push the new code?
I can log on those machines and update each of them.
Yes, that would work. But let's scale a bit. Let's assume your service is running on thousands of machines. How would that work then?
Well, I'm an engineer. I can write a script.
Yes. Let's assume we have multiple services owned by multiple teams, and all of them have different release schedules.
That is hard. Well, maybe I can write multiple scripts.
Yes, but then you also have to sync up with all the teams about the release process.
That is true.
And what if something goes wrong and you need to revert?
That is a hassle.
Yes, and these are only some of the challenges we see at scale.
In this presentation, we would like to talk how we do continuous deployment at Facebook, where we have thousands of services running on millions of machines.
You might be familiar with the old Facebook mantra, move fast and break things. This allowed engineers to move fast because the quicker you get feedback on the things you built, the sooner you can improve it. However, as more people rely on the products we build, the price of making mistakes goes up, and we no longer have the luxury of breaking things. Furthermore, as the company scales by adding more engineers, machines, it becomes increasingly inefficient for humans to manually test and deploy code. And because of this, we absolutely need to automate testing, building, and deployment. And as the ability to move fast continues to be the priority, the company has invested a lot in building the necessary infrastructure. Correspondingly, the Facebook mantra has changed to move fast with stable infra.
Last year in this conference, Anka talked about how we solve this problem on the web tier. For engineers who work on the web service, they just need to check in their code, and our automation system will pick up the changes, run all the unit tests, and take steps deploying to the entire fleet. Well, this happens multiple times per day. This is how our engineers can code in the morning and have it to be used by over 2 billion users in the afternoon. However, that's not the case for everything at Facebook. We roughly divide our services into two categories. We have web service. It's homogeneous. It's just PHP. Everyone works towards the same product. It's easier to have a team taking care of the deployment. And then we have everything else on the back end. They are all different in terms of the number of machines, machine types, business units, and the release cycle, you name it. And it's very hard to find a group of people knowing all of them and then deploy the changes everywhere. So instead of having each team building their own release tool, our team built a system called Conveyor that will solve the problem for everyone.
Yes, and if you haven't guessed it yet, the name Conveyor comes from the conveyor belt, where you kind of have packages moving from one stage to another. However, before going into details of Conveyor, let us take a step back and take a look at the typical release process. Firstly, the code needs to be built and packaged into some kind of executable. This is followed by a testing phase where we want to make sure that our changes do not cause any regressions. Finally, after the testing has been completed successfully, we want to deploy to production. So we have build, followed by test, followed by deploy. Now, let's take a closer look at the build process. The typical developer experience involves write some code, test locally, submit for review. However, how many of you were in a situation where you wrote some code and you thought you run all the tests, but you actually missed a few? This happens to me all the time. And when working on a large product, sometimes it is hard to determine all the tests that should be run in order to test your changes. This is especially hard when working on a shared library because dependencies aren't always clear there. And because of this, at Facebook, we have a system called Sandcastle that automatically determines all the parts of the code bases that are affected by your changes and run all of the corresponding tests.
So once the code is reviewed and tested, it's checked into our latest repo. And our Sandcastle system will periodically fetch the changes and builds all executables.
Yes, and we mentioned Sandcastle now briefly. So Sandcastle is Facebook's automatic build and test system. It consists of a pool of machines where every machine has the latest snapshot of the repository checked out. Hence, it can quickly patch changes, run tests, and build executables. The graph presented on the slide represents the trend of Sandcastle building executable and running affected tests per hour. And this needs to happen thousands of times during peak work hours. And because of this, we have a dedicated fleet of machines just for this kind of work.
Once the executable is ready, the next step is to test it. All right, let's be honest. How many of us had the following experience? We wrote some awesome code. It can be either a hotfix or a cool feature. We thought it's straightforward enough. We rolled it out, and disaster happened. Okay, for the ones who did not raise your hands, I have a personal suggestion. We only live once, you need to try harder. For the ones who raise your hands, I guess we'll agree that testing is important. We will spend some extra time talking about it, because this is why our auto-release is safe. One common testing process in Facebook is Canary.
Fangfei, what is this bird about?
Well, this little cute yellow poor bird is Canary. In the old days, miners used it to detect dangerous gases. If the environment is unsafe, then this bird dies first.
Ah, I see. Okay, so similarly to that, Canary, not the bird, but the testing process, is used to test changes only a small subset of machines, and then if something is wrong, we abort.
You got it. So let's take a look at the high-level design. This graph shows the traffic flow from our users to the backend service. Our users send traffic to the service, to the web servers, and our routing system redirect them to the backend machines. At Facebook, vast majority of those machines are maintained by a container system called Tupperware. Kenny from Facebook will talk more about it later today. For now, let's just consider it as an internal version of Kubernetes. Those services log various metrics that are consumed by health check service. So to start a Canary, the Canary service integrates with Tupperware to load the new code on some of the machines. Then it constantly checks if the service is healthy. If it's not, then it cancels the Canary.
Let's talk about the life cycle of a Canary. The life cycle can be roughly divided into 3 phases. We have startup, running, and teardown phase. Startup phase involves restarting the container with the new version of the code. After this, we are monitoring the service to make sure it comes up fully initialized and ready to serve traffic. On the other side, we have a teardown phase where we want to revert this. So we want to restart the containers with the original version of the code. Once we do that, we're still not done. We still want to make sure that service comes up back fully initialized. This gives us a nice signal on whether our changes are backward compatible.
Okay. Those 2 phases are important, but the most interesting part is the running phase. This is the main phase of Canary, and this is where we run more complicated checks to make sure the new code does the right thing. One of those checks is health check. Service owners define a group of metrics and the threshold to represent the health of the service. During a Canary, we constantly check if the service is healthy. If it is through the end, then we consider Canary as a success. If at any moment the service is unhealthy, then we abort the process.
And another testing feature we support is load testing. Our internal routing system can steadily increase the traffic to a particular server until it reaches the capacity limit. This allows us to measure a few things. Firstly, it allows us to measure the maximum throughput supported by one server. Also, it provides us insights into whether our changes caused any performance regressions. Finally, we can use this to estimate the number of machines our service actually needs.
Okay, so far we have been talking about testing on production tier. It's easy to set up, but it does involve some risks. Therefore, we also support testing in asset environment. One way to do that is Shadow Canary. It's very similar to Canary process, but Shadow Canary sets up temporary machines, and our routing system duplicates traffic to those machines for testing purpose.
But how do you make sure that these shadow machines do not pollute real data?
That's a great question. Shadow Canary provides an environment variable, and inside the service, if this variable is set, then it doesn't write to database or sends out traffic.
And yet another approach available for canaries is synthetic test, or better known as record and replay. In this scenario, the traffic to a service is simply recorded and saved for the later use. Then during the testing, the traffic is replayed and outputs are observed for comparison and correctness.
All right, everything we have seen till now was designed to build our confidence for the new code. Now let's assume the new code is well tested. The last step is deploying it to the production tiers.
But that should be simple. We just restart all the containers with the new version of the code.
No, if you do that, we're going to lose Facebook.
Oh, damn it. Okay, so how about this? We need at least one machine running even during the push. So we need at least 2 machines. So we can update the first half of the machines, wait for that to complete, and then update the second half.
This is better. I think it probably works for small services. But for large services like Messenger, losing 50% of service is still a big deal.
Okay, so we need to do smaller increments. So instead of having 2 phases, we can have multiple phases, and we can actually make this configurable. So service owners can define how many phases they want and how big is each phase.
Okay, but what if something goes wrong in this process?
You mean if we find a mistake in the code that we didn't find during the testing?
Yes.
Okay, in that case, instead of immediately advancing to the next phase once the previous phase has completed, we can add a baking time in between. During this time, we can monitor the service to make sure that nothing is broken.
What if something is broken? How would I know about that?
Well, in that case, we can build a notification system, and we can notify service owners when something is wrong. We can include plenty of information to make their debugging easier.
But I want this to be a hands-off experience.
In that case, we have to handle failures better. We should automatically retry all the transient failures, and if we cannot fix the problem, we should automatically revert to the previous version.
Okay, what if I have 100 machines, and 99 of them updated correctly? Only one has problem. Are you going to reward everything?
That's a good point, and this is statistically unavoidable for big services. So how about this? We introduce a maximum failure limit, and as long as the number of failures is less than this limit, we keep pushing. Does that work?
Sounds good for now. I'm pretty sure there are more things we can do better, and if this problem sounds interesting to you, come to find us afterwards. We'd love to chat. Now let's take a look at the implementation. You may find this image very familiar. Yes, it's the same setup as for Canary, but instead we have a push server that integrates with Tupperware to update the machines at each phase. Then it continuously checks if the service is healthy. If it is not, then it cancels the next step.
Yes, and the push server actually consists of 2 parts. One part is responsible for moving the push from one phase to another. The second part integrates with our container system and is capable of issuing updates to the service. But because of this setup, we can completely replace the second part with some other container system. And this means that our engineers can use the same push process for a completely different use case. For example, using Chef to deploy RPMs.
Okay, we have covered a typical continuous deployment process. Now let's take a look at how we do everything on our conveyor system.
Yes, and let's talk about the design principles. The first design principle is simplicity. Given that conveyor is used to deploy thousands of services, which in turn are maintained by thousands of engineers, it would be unreasonable to expect all engineers to be well-versed into details of continuous deployment process. And because of this, we work hard to maintain simplicity. Once you know the few basic things about Konveyor, you should be able to start using it. To illustrate this, let us take a look at the typical release process. Here, we have a Konveyor config. At the top, we have something called service ID, which tells Konveyor what code to test and where to deploy it. This is followed by a series of operations we call nodes. Here we have build node, canary node, and push node. You can think of a new code flowing from top to bottom and stopping whenever it encounters a failure. If you are a new service owner, all you have to do is just write a simple file like this, and it will be picked up and executed within minutes.
The default steps provided by Konveyor may satisfy most of our users. But what if a user wants to customize the process? For example, a canary may produce a lot of data, and the users may want to analyze the data to make sure the new code meets the standard. To that extent, Konveyor was designed to be flexible since beginning. The way Konveyor interacts with Konveyor node is very straightforward. Here, Konveyor node represents all the subsystems like canary or push we just talked about. Konveyor sends a request in the beginning, then it keeps polling the status until it's finished. If a user wants to cancel the process, Konveyor also forwards the request to Konveyor node. Having that said, for each Konveyor node, they just need to implement the 3 functions. And we implement the default ones. If a user wants to add a customized node, all what they need to do is set up a service implementing those 3 functions, and Konveyor takes care of the rest.
The last piece I want to talk about is the importance of standardization. As Fangfei has mentioned, each Konveyor node maps to a stateless service that focuses only on the actual operations. All nodes implement the same API. Because of this, every Konveyor node gets plenty of benefits that come for free, such as scheduling, storage, scaling, and notification.
Okay, now we know how Konveyor works. How does it do compared to similar products in industry? We did some high-level comparison, and the good news is we found Konveyor is very close to industry standard from many perspectives. It provides CLI and UI tools. It supports notification, monitoring systems. It offers deployment strategy. It allows integrating with multiple container systems. Now, how many of you have used Jenkins? Okay, Jenkins is plugin based. Users can use it for various processes. It doesn't have to be for deployment. While Konveyor was specifically designed for continuous deployment, it allows some customization, but it always starts with build and then ends up with push. How many of you have used Spinnaker? Not many, great. I can say whatever I want. Konveyor is very close to Spinnaker, but you can invoke Jenkins or other third-party systems through Spinnaker, while Konveyor was designed to integrate well with our internal services. From that perspective, it has suited us the best so far. Konveyor has done pretty well for our backend services since we launched it. This graph shows the trend of the number of services using the 2nd generation of Konveyor in the last year. Right now, we have about 70% of services using Konveyor for deployment.
Yes, but there's plenty of work ahead. We expect this number to grow maybe to 98%, but the last few percent is going to be very difficult. Just last week, we had a meeting where a team has hundreds of thousands of jobs, and they want to onboard everything to Konveyor. And the first thing that came to my mind during meeting is, what will break first? Will it be the load on the database? Do we need to redesign our scheduling scheme, or something else?
It could be everything. We don't know. There's a lot of work ahead.
Yes, and talking about the work ahead, let's talk about the future work. At Facebook, we want our engineers to spend most of the time solving real problems for our users. Hence, we want to take care of the most of the operational cost that comes with building and maintaining services. So we work hard to improve the developer experience by providing the signal about correctness and performance as soon as possible in the process. And this explains the intent to better integrate Konveyor into our code review tool.
And as I just spoke of, right now we have about 70% of backend services using Conveyor. There is an effort driving this trend to be 100%. But shall we even do that? It's an open question, because some mature services already have a very tailored release process for themselves. So forcing them on Conveyor may not be the best choice.
And finally, the Conveyor, although not a general workflow system, can map to some other concept, like continuous deployment of machine learning models. And in order to not reinvent the wheel, we're exploring supporting these use cases as well. Whew, we talked a lot about in this presentation.
We did.
And this finishes the overview of continuous deployment at Facebook. This is how we deploy at scale.